Okay, I think we should start. Let me just pull this out of the way. And, and I should warn you that the Bayesian models of Bayesian cognition lecture is the cursed lecture every single year. So the first year I recorded it without the slides. The second year I recorded it without the audio. The third year I forgot to turn it on again after the break. And this year, I was revamping it completely with a whole new model. And my kid number one got sick. My kid number two got sick. And then I got sick. So I hope that should cover the curse for this year. But some of the slides are not finished, but I think that those are the slides that we'll cover next week. So I'll manage to finish them. Good. So what we're going to do today is you were expected to have gone through the model comparison lecture and the course notes. And I have an overview slide, but I would actually want to have your question and doubts and stuff. Then we will be trying a slightly different approach to cognitive modeling than what we've done before. So before we took a task, and in a very ad hoc way, we built up models of how we could solve that task, invoking cognitive principles as needed. This time, what we're going to do is we're actually going to start from a cognitive principle, the idea that the mind might work as a Bayesian machine, like a machine that integrates information of different kinds. And then we'll see how we can apply that model to different contexts. We will be working on a concrete example integrating direct and social information during the lecture. And for the assignment, you will have to apply one of the models or two that we're working on during the lecture and apply it to a different experiment with a different structure. So, and then we'll see some code, and some of that will fluctuate to next week. So the first thing is, do you have questions on the model comparison stuff? Yes. Yeah. The log posterior probability. Yes. Yes. Yeah. Let's call it min error. Yeah. Cool. I think I'll just go around and see if there's other questions, and then I'll tackle it. Yes. Log posterior probability. Yeah. Yes. Instead, they want log like. Yes. They would be. But yes, this is a good question. I'll tackle it as I tackle that one because they are very correlated related. Yes. Hmm. Mm-hmm. Mm-hmm. Yeah. And so these would be when you say the weighted models, that's the when you calculate model weights based on the leave one out. Yes. Okay. You're not talking about the mixture models. Yeah. 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 Yes. Yes. Yeah. Mm-hmm. Was that the Pareto smoothing? Is that what's missing there? Yeah. Yes. Mm-hmm. Okay. Yeah. Good. Yes. Mm-hmm. Yeah. Okay. Yeah. Okay. I think I'll make a note. I don't remember that part, but I'll have to go and check. Yeah. Is it mentioned in the course notes? Because I've rewritten them quite extensively. I don't think I use that term, right? Yeah. Yeah. I'll need to check. Yes. Good. Yes. Mm-hmm. Yeah. So posterior samples cannot be the same for the different models, right? Yeah. Okay, now I get it. Yes, perfect. It's actually in the test performance. Great. I'll actually cover it. Good. Yes. More questions? Yes. Mm-hmm. Yeah. Yes. Good. So I have a slide of overview, and then I'll try to cover these questions as we go through the overview. And then you can come up with any additional questions you have at any point. So the idea is that that the model calculates something that's called log posterior probabilities for each data point for each sample, right? So what we do is as we're moving in the posterior space with the Hamiltonian Monte Carlo sampler, right? If you remember, at any point, we calculate how likely are the possible, well, actually, we have a combination of parameter values, and we look at how, now I have to get it right, how likely the data is given these parameter value, right? Or in other words, how probable this, I got it. How probable the data is given this parameter value, which is how likely these parameter values are given the data. Right? And that's what gets stored in the LP. And if you remember how the Hamiltonian Monte Carlo works, right? In the Hamiltonian Monte Carlo, we don't have a separate prior and likelihood, right? We set the priors, but then what we do is that as we calculate the how likely the parameter values are given the data, and I'll keep getting that wrong, but you understand what I mean? Uh, we include the prior information, right? There's something called target that tells us in the model all the different components that get included in the log posterior probability. And given that very value, our trajectory in the Hamiltonian Monte Carlo is shaped, which means that we don't have a likelihood estimation that's separated from the prior, because the prior is influencing how we can explore this space. And in that sense, people have been quite loose in terms of what, if this is log posterior or log likelihood, because in the Hamiltonian world, there is no real difference, right? Because they're all enmeshed with each other. So the log posterior probability that gets saved is something that says, if we take these parameter values and the equation of the model and we generate 10,000 predictions, how many of these match the actual data? And in that sense, the more match the actual data, the lower the error of the model, if you want. The fewer match the actual data, the higher the error of the model. Right? There are certain data points that are really hard to imagine would happen if these models were true. Right. Then we take that LP variable, right? And what we can do is we can say, well, we know. Do you remember? Did you do AIC and BIC in methods 3, I guess? Right. So when you calculate how well a model fits the data, right, you need to consider that the more parameters you have in your model, the more likely it is that the model can describe your data, but that wouldn't generalize to new data. In other words, that you're overfitting to the data. And so the AIC, I can't remember, but the exact formula in this moment, but it has something like it's calculating the likelihood, right? And then it's penalizing it with a certain, I think it's 2 times the number of parameters, right? So yeah, it would be 2K. And the BIC is doing something similar, but it's penalizing it with 2K, and that's also with the number of data points that you're using to fit the model, something like that. So also when we calculate a proper performance of our model, we want to take into account that the log likelihood or log posterior might be overfit to the data, right? We want to ensure that we're not just looking at fitting the signal and the noise in the data, but we want to ensure that we have a good estimate of how well would this model perform if we were to meet data that are similar to this. Right? And so what we want to do is we approximate what is called the leave one out posterior probability, log posterior probability, right? By doing a certain trick. So usually what we would do is we would take one data point out, fit the model, then predict the data with the model and see how well it does and repeat for all the data points. Or if we're slightly more sophisticated, what we can do is we can take the structure in the data, let's say the participant level. Right? We take all the data from one participant out, we fit the model, we test on that participant, and we repeat that for all the participants. In the Bayesian world, that's still an ideal procedure, but given that the models can take a few weeks to run, right, that's really not something we want to do too often. So what we want is a procedure that approximates that specific way of thinking, right? How probable the single data point would be given the model that we have, right? Assuming that it wasn't trained on that data point. And so what it does is it actually says, let's look at data point 1 and let's look at how probable it is given the model, or given actually not the model, but the data set. Right? So if we have, right, let's say we're looking at reaction times, we have that most people respond within 1 second with a peak at 800 milliseconds, right? If we get a data point that's 800 milliseconds, 820 milliseconds, it's very probable given the data. If we have something that's like 3 seconds, it's very improbable given the data, right? And so what we say is so we assume that if the data point is similar to most of the data, it will be well described. So it's not going to be very informative. If a data point is very different from the rest of the data, that might tell us something about what would happen if we apply the model to new data. Because as we sample the possible data, this is the universe of possible data, right? We run our experiment, and it might be like this, right? But we are quite sure that with the limited amount of resources of a normal experiment, or even looking at all the patients with depression at a given psychiatric inward, right? We will not capture the full spectrum of depression, right? So if we were to collect a new samples, right, we would likely do something like that. And so the points that are on the border that are far away from the most probable points, right, are more likely to represent our out of sample performance. Does that make sense? The intuition? Yes. And so what we do is we say the probability of the data point given the rest will inversely weight how much the log posterior probability should count. If it's a very probable value, it shouldn't count for much. If it's a very improbable value, it should count for more. Right. So was there something there on this? Not yet. No. Okay. So it is a strong assumption. It is a conservative assumption that says, well, actually, let's have the data points that don't fit very well drive our estimation of how well this model is performing. Then there's something that the model does that's, with a finite amount of data points, you'll have a bunch of weights, low weights at the beginning, and then you have a few weights in the tail, right? Some data points that are hard to fit. And that tends to mess up the estimation, because how do we figure out the long tail? And should one data point really be overwhelmingly determining everything? So what the Vetari group in Finland has devised is a Pareto smoothing. So they fit a Pareto distribution, and then they readjust the weights to fit the Pareto distribution. And that gives a much more stable reweighting of the log posterior probabilities, right? So now what we have is we have that for each data point, we have a distribution of log posterior probabilities, right? Given all the possible posterior samples. And we have a weight. We can then calculate a estimated predictive performance, leave one out, predictive performance of the model by doing these weighted average, right? And combining all the posterior samples and all the data points. Or what we can do is we can separate data points by data points or participant by participant or condition by condition and get separate estimated predictive performance by these different clusters of data. Yes. Mm-hmm. Yeah. Mm-hmm. 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 Uh, yes. So the way that the formula is derived is exactly what you're saying, right? That the outlier would represent a bigger error. And well, it depends on how many data points you have, right? Because if you have few data points, the outlier is going to overly influence the model. These explanation is saying a consequence of that way of thinking of the Brackett's outliers is that we can start accounting very partially for what is called distribution shift in machine learning, right? The fact that the data that we sample are a subset of the full possible sample. So this is not to derive the formula. It's actually a conceptual implication of the formula. Yeah, good. Then what we do is we can take these values that we got, the expected log predictive density, I think, and we can compare two different models, right? We can say, now we have a distribution of these ELPDs, and we can say, well, model one has an average of, I don't know, -5,672, and model two has an average of -3,521. And given we have a distribution, we can also get a standard error, right? And if this is something like 10,000, that's really bad because even if one is clearly lower than the other, the uncertainty doesn't enable us to say anything, right? It just means that they're really having trouble describing a lot of the data points, both of them. If it's something that's small, let's say 20, right? Then with these different, it seems that we can actually start relying on the difference. Alternatively, what people have been doing, especially in a predictive fashion, is maybe actually we don't care about picking one model, right? I like the Macabrith metaphor. That's like if you have a bunch of horses that are running a race, right? One of them wins. You don't shoot the other one because they're useless at running, because next time they might get slightly better. So what you can do is you can calculate the relative weights of the two models, right? The conceptual explanation of the weights is if we were to predict a data point and we outputted the prediction of the two models, right? How should we average them in order to get the best prediction, right? Where should we put the higher weight, right? We might have that one model is consistently more reliable. We give it a weight of 0.8, but sometimes the other is right? So it gets a weight of 0.2. So it adjusts a bit the prediction of the first. And that's where it's used. So one of the reasons it was developed, it was a project trying to predict the properties of concrete, mixing different proportions of ingredients. They made different models of the process. And then what they really wanted was knowing how, well the concrete would resist to different torsions and pressures. And they didn't care about the specific model. So they just created a set of weights and optimized in terms of getting the best prediction. Alternatively, right, what one could do is one could do the same kind of process by participant or by condition. And that's a good way of trying to identify participants, data points, structures in the data that are described differentially well by different models. This is the only place I've been using it properly. I've been seeing use it properly was in ecology, in a study on different kinds of primates where there's a population of lemurs that just doesn't follow the usual ideas on sociality and the impact of sociality on brain size. But it is something that is really up there for the taking. Sometimes what we get is that a lot of the data points are not really on these Pareto distribution. They're just higher, lower, and so on. And what we then have is the diagnostics of Lou that says, watch out, your Pareto K, there's these many data points with a Pareto K above a certain threshold. That means that the assumptions that we're making are not likely to well describe the way that the model works, right? There are too many outliers to actually work with the smoothing that we're doing. So what we might want to do is we can run actual cross-validation. That is, we know the structure of the data, we set it up. Let's say in our multi-level models that we ran so far, it's the participants, right? We say, let's do 5 folds. Each fold contains an equal amount of participants. We train the model, we fit the model on 4 of the folds. At this point, we have a fixed model, right? That's where the fixed posterior come. We're not training anymore, right? But we can still see, given these parameter values, how well the data points in the test set, in the remaining fold, work, right? How likely are we to generate those data points if we were just to run simulations from the model plus posterior parameter values. And then we repeat that for every fold, and we have a new set of ELPDs that we can use to calculate the weights and to do the Pareto smoothing and to run the model comparison, either straight on the estimated expected log posterior predictive densities and or do the model weights. And the remaining question that I had is, could we run the model separately, identify weights, and then use them as prior for a mixture model, right? And that's double dipping, right? You're doing it on the same data. So it might make sense if you're then, okay, we've run these study, right? We didn't know about mixture models. We did model weights. Well, next time we run a study, we're going to use these model weights as a prior for a mixture model that will be fit on the new data. For those of you who haven't looked at the mixture models, the basic idea is that now we're doing model comparison, fitting the model separately. Bayesians are megalomaniacs. They really like to have everything within the same model. So there is a thing called mixture model that basically says the log posterior probability is given by function of the probability of model 1, right, times model 1 plus 1 minus the probability of model 1 times model 2, right? And it says, and now estimate the probability. All right, so data point by data point, it will go through and say how likely is these model to generate the data point, how likely is the other model to generate the data point. We put it on a 0 to 1 scale where the respective probability sums up to 1. We use those estimates to further steer our Hamiltonian path in the posterior space. If we have more than 2 models, we just need to make sure that the different probabilities sum up to 1. And then at the end, instead of having the model weight or the ELPD, what we have is an actual distribution of probabilities that model 1 has generated these data, that model 2 has generated these data, right? Or alternatively, depending on your conceptual question, which proportion of the data have been generated by one model and which proportion by another. So a clear example that I've actually used a couple of times is attentional lapses, right? So we know that people tend to get distracted. We know that there is noise in the data, right? We might make our model a mixture of the model that we're interested in plus a uniform distribution of reaction times where people are just doing some random shit. Or in the matching pennies example, we have, let's say, the Winds-Taylor shift and a random agent just overlaid to each other. And that way, for instance, instead of removing data points that might be outliers, right? Too fast, too slow. What we have is an additional parameter that can help us describe the condition or the participant. That is the propensity to have attentional lapses. But they're a bit tricky to fit, especially as we get to more complex models. So I've sort of taken that lecture out of the normal thing because we don't get to have enough time to actually fit models with a big mixture. Good. We'll see an example next week on how we run model comparison using Bayesian models. Are there additional questions? Good or bad? We'll see. Questions can come at any time. There's the question and answer doc. Again, I haven't looked at it today, but I tend to look at it a few times a week. Last time I checked, there weren't new questions, but they're very welcome to appear. We're now moving to the next chapter of the course, which is on Bayesian models of cognition. And I've taken broad inspiration from two books, one that came out a year or two ago, I can't remember, called Bayesian Models of Perception and Action, that goes really nitty-picky into how we can model very basic perceptual and motor processes using Bayes. And there's a new book that came out recently, which actually has the broader picture on, if we take Bayes seriously, we can reverse engineer how the mind works. And I think they're really good modeling books. As you go through them, you can also see that there are limits to using one model to describe the mind, but that's a different philosophical thing. I'm actually reading the Bayesian models of cognition now, and I'm really, really enjoying it. So, Bayes rules, right? But basically, the probability of A given B is equal to the probability of B given A times the probability of A divided the probability of B. If you're like me at this point, you just what? Right? I thought I knew that, and now you just lost me. So usually the way that we have is we want to know the probability of a given theory, a given explanation, a given, if we're talking about perception, that what I'm seeing is Balázs and not somebody else, given the kind of input that I'm receiving, right? And that is calculated by A, right? Even before seeing the data, how likely it is to see Balázs. If I'm teaching advanced cognitive modeling, that's quite likely, right? If I'm in the room where I'm teaching social and cultural dynamics, that's much less likely, right? Times what we usually call the likelihood, right? How likely is the data given the explanation? And see, I got it wrong again. I can never remember which one is probable and which one is likely, but here is right. So how likely is the data given the explanation? And since we are working in probability space, right? Let's say that the probability of Balázs being here is 0.8, right? And the probability that given what I see, this is Balázs, right, is 0.6. When I multiply them, I get 0.48. And it's not clear if it's a 48% probability or if it's just multiply, because it doesn't really make sense, right? 0.6 times 0.8, it should be higher than 0.5 at the very least. So that what happens is that because we need to normalize these probabilities into a space 0 to 1, and we do that using the using the probability of the data independently of the explanation, which is a trick that we use to make the posterior probability density sum up to 1. These kinds of plots, right? So we have a prior here. We have a likelihood in red, and the evidence contained in this distribution gets put together. The idea is that the Bayes rule has been developed by Reverend Bayes and by all the people, because he never really published the manuscript, right? So he was a priest of a sort who, since at that point when you were a priest, you were just basically staying in your home and writing whatever interested you or hunting bumblebees or whatever. And then one of his friends, actually, before even publishing anything, everybody thought he was very smart. So they induced him into the Royal Society, which is very prestigious. And then after his death, one of his friends found a box with some notes, including the manuscript of Bayes' theorem. He decided to rewrite it. He didn't have ChatGPT at the time, so he just used his brain to rewrite it in a better way and more interpretable way. And we actually don't even know what Bayes really said and wrote at that point, because we only have this completely rewritten version. And his point was that this theorem allows you to integrate two sources of information. It's the rational integration of two sources of integration. If this is what you know before, and this is what you see, the optimal way, the optimal inference that combines these two informations is the posterior. Right. These has been applied to model fitting and parameter estimation. You've seen it in methods 4, but also in this course. The idea is that you have a certain prior. We always need to define the priors. We have a certain likelihood, and then we use Hamiltonian Monte Carlo tricks to do the normalization, so we don't need to worry about that. And then we get a certain probability, right, of the parameter values being what they are, or of model 1 being better than model 2. However, it is also being used as the model of a computation performed by the brain or the mind. We have the probability of a certain model of the word given the sensory data, and we can explain the kind of perceptions that we have by rationally combining the probability of the sensory data given our theory, the probability of the theory or of the model of the word that we have, and dividing it by the probability of the sensory data. And so the belief that we should have in a given explanation is given by multiplying the evidence presented in two sources of information and normalizing it. Technically, there is no reason for which there should only be two sources of information. The math doesn't care. This model is very easily extended to just multiplying all the sources of information and renormalizing it, which will come in handy. So how does this describe cognition? And here is a very simple example. I turn that off. Do you know this illusion? Yes. Right. So if you look at it, some of the dots look as they are concave and other as if they are convex. Which ones are going inside? Yes. Okay. Do you have the same? Yeah. Why? Yes. Yes. Right. So we have experience of the word where most often light comes from above. Therefore, the fact that there is light here tells us that here there is an edge and something going in, so it's in shadow, and here is the opposite. Right? There's something coming out so that this part can be in shadow. There is no reason from the pure likelihood that some should be convex and some should be concave. Right? So we have an internal model of the word that defines the prior, right? And there's a state of the word outside that, depending on the sensory modality we are in, let's say we're talking about sight, there's some proximal stimulation, photons that have been reflected by the object in the word that hit our sensory system. These two get combined. Actually, if we take modern approaches to perception, not only combine, but these two guide the way that we explore the word to improve on our sensory stimulation. And these process temporally extended gives rise to the percept, right? What we think we're seeing. These kind of ideas has been explored in a very wide range of phenomena, especially how do we gain information about the word? How do we go beyond all theories of tabula rasa, right? We are born not knowing shit. And equally crazy theories of we are born knowing a lot about the word, right? We are born having a language module in the brain, right? That we just need to shift into some specific language. And so the idea is that we can have a bunch of different vague structures. So for instance, here is how do we learn whether, um, it's best to think about animals as a tree or as a chain or as a ring, right? We might have some ideas about these possible structures in the background. They have each a prior. Each of these structures then has different ways in which they can configure themselves. The ostrich might be close to the mammals or might be close to the birds, right? And we can have these two layers of probabilities that as we encounter more and more exemplars in the world, we can update our prior probabilities of the meta structure that we should apply to this domain, but also of the specific structure that best describes the data. And that's also been applied widely to how children might learn words. For instance, this is a very famous experiment. They show some previously unknown shape and say, this is a ducks, right? And then they show them different objects, some that have the same shape but different texture, some that have the same texture but different shape, and try to see which children generalize the name to. And again, that can work over time, having priors for the shape, determining the ducks, the different materials determining the ducks, and the importance of shape and materials. And if you want more of that in the book that I was mentioning before, they have a few hundred pages on that sort of models, right? And I'll stop here and we'll take a break. Yes, 10 minutes, and then we'll continue on how this explains different parts of our experience. Okay. So, whoops. So the idea in these models of, for instance, perception and cognition from a Bayesian perspective is that our experience is a blend, right? We have that the word is very rich. Proximal stimulation, so what hits our eyes or ears or haptic sensors or what have you, can be generated by many possible underlying models. And priors, our expectations, can help us regularize our experience of the word, right? So that we don't have this shifting percepts of all the possible sources of these data, but we actually have quite reliable experience of the word, right? As we are looking at a certain person, even if, when they turn in a different angle than we have seen, they might look like somebody else, right? We keep perceiving them as the same person. At the same time, we have that our imagination is rich, right? There's many possible words inside. And proximal stimulations, right? The sensory stimulation can help us making perception and thought more regular and boring and reliable, right? One of the potential explanation of the specific phenomenological quality of dreams is that they're not stabilized by sensory stimulation. So they sort of much more drifting than our wake experience. These has been used to try to explain some of the atypicalities in different neurodevelopmental and psychiatric conditions. For instance, there's Bayesian explanations of autism. I think the main dominant one is that they have hyper-precise prior, so they get errors all the time, and that could lead to sensory overload, right? These theories explain certain interesting phenomena. They're not overall explanations. We have that in psychosis, the prior, actually, yeah, in this paper, they claim that the prior might be overloading the sensory process, giving rise to hallucination. Actually, there's other papers that I read more recently that claim the opposite, that is just not stabilizing the sensory information with your priors might lead to hallucinations. But in general, there is an attempt at saying how far can we push this model to explain the broad variety of experiences that humans have. And so, however, right, while we can focus on the perception as the most obvious case where we can apply this model, Bayes' rule doesn't care about which kind of information is involved, right? We can have priors and sensory stimulation, but we can have also two different sources of individual information. So let me see a second if I can. You probably know this one. No, it's still going to my ears. MacBook speakers. Maybe I can do this one. Nope. And I'll turn this off.
Ba, ba, ba.
Have a look at this.
Ba.
What do you hear?
Ba, ba, ba. Ba, ba, ba.
But look what happens when we change the picture.
Ba, ba, ba. Ba, ba, ba. Ba.
And yet, the sound hasn't changed. In every clip, you are only ever hearing ba with a B.
Ba, ba.
Yes. So the basic idea is that there's a ton of studies, for instance, on how we disambiguate different sensory stimulation using multiple. Just need to, yes, this is in place, using multiple sensory information, multiple modalities. For instance, here we have that the way that the visual sensory stimulations are shaped and configured defines partially what you hear, right? And so in this sense, the Bayesian model doesn't need to actually have prior and likelihood. It could have two different sensory sources. And if we take humans, humans do not just rely on their multiple senses, but they are deeply social. And I think that's where there's a very interesting application of Bayesian models, right? We've said that Bayes' rule doesn't care about the nature of the sources. So we have an additional source for our learning how to interact in the world, which is social learning. We continuously supplement our experience of the world via social information, right? So we can see whether Bayesian models can explain the way that individual experience and social information get merged. And just to riff a bit on what I was saying before, right? The world is vast and our imagination is even more. Other people allow us to constrain the domain of possible explanation, right? We have traditions, we have social learning, right? When a kid hears a noise and says, "What's that?" you can actually tell them, "Well, actually, that sound is a monster in the wall," right? Traumatizing your kid forever, but being very effective in shaping their experience of the world for, long many years. So this is something that has been researched quite a lot. So for instance, here is an attempt at seeing which domains and forms of inferences are shaped by social information in schizophrenia in a different way compared to non-schizophrenic individuals. And really, we can have that we have the individual information can be added to the social information from source one to the social information from source two and blah, and we can still keep using the same conceptual and mathematical framework. So let's see an example. This is something that Bayesians and people who do Bayesian models of cognition love because it's really easy to model. It's an urn, and inside the urn, I think it's called technically a polia urn, and inside there's marbles of two different colors, green and red in this case, very colorblind and friendly. And the task that we ask our participant is, what color is the next marble, according to you? So we can have two sources of evidence, right? We have a prior, right? We can know that 2/3 of urns just like this contain more red marbles than green marbles. Or, my friend sampled 3 marbles and tells me that 2 are red, right? It doesn't really matter the source. We can actually have this prior information there. Then we have a likelihood, which is I now sample 3 marbles and 2 are red, right? 2 out of 3 is 0.666666666 periodic. We need to combine the two sources of evidence, right? It's clear that I have now more evidence that red marbles are more likely than green marbles, but we want to put some math on that. The idea is that we can take Bayes' rule as optimal, right? Each source of information tells us something about a possible binary choice. There is a probability between 0 and 1. Each source of information is optimally combined, that is taken at face value. And so what we can do is, here using the binom, I draw the prior given 2 out of 3 being red. I draw the likelihood, the distribution of underlying rates that we can infer when 2 out of 3 marbles are red. It's exactly the same, right? And then we combine it, right? And we get that posterior. And so what happens in that posterior? What changed compared to the prior? Yes? Yes. In a sense, right, we see 2 evidence sources telling us that it's more likely for red to be the next marble, though it's not 100%. We see that the peak is more or less the same at 0.66. And we see that the variance has shrunk, meaning that we have a much smaller belief that the next marble might be green. We also have a much less belief that it will always come out red, right? Because we've seen twice that it doesn't always come out red. And these 2 aspects are actually quite important. So, because it really has an impact on how we implement those models. So the first is something that's very common in the literature, which is we can simplify our life relying on log odds, right? We know that log odds have lots of nice properties. They always turn our outcome into 0 to 1. They're on a log scale, so we can sort of simplify away multiplications by doing additions. And so we can say that both sources say more red than green. The agent is therefore more likely to say red, right? So what we can say is that the logit of the posterior in terms of log odds, is equal to the log odds of the probability of the log odds of the prior plus the log odds of the posterior, or of the likelihood, or the log odds of our agent's belief in the next marble being red is equal to the log odds of the evidence from source 1 plus the log odds of the evidence from source 2. Which is, right, log odds of 0.66 plus log odds of 0.66 is equal 0.69 plus 0.69, which is equal to 1.386, which, if we invert logic, tells us that there is a probability that the agent will pick red with an 80% chance. Right? This is, to a certain extent, satisfying, right? To a certain extent, it's dissatisfying. Why? Because what we have is that if the two sources say 0.66, right, we might have that the agent will keep the 0.66 somehow, right? But what this is saying is the agent will be more likely to pick red, which under a certain conceptualization makes sense. We might disagree with that and therefore try a different way, which is both sources say 66% chance of red. The agent reinforces the belief that the underlying rate of red is 0.66. Right? It's not about the binary choice. It's about the belief in the underlying rate. And this could simply be made by doing a mean of the two, right? So we say it's exactly the same equation as before, but we say that source 1 has a 0.5 weight and source 2 has a 0.5 weight. Then we can solve it. 0.5 times 0.69 plus 0.5 times 69 is exactly 69. And that gives us 0.66, right? And so according to how we choose to conceptualize the task that we're giving our participant and their underlying cognitive mechanism, we can use log odds to create a model that reproduce the behavior that we think is interesting, right? And skipping many slides ahead, right? You could say, well, and then we can simply put this as a weight that we want to estimate. And then the model fitting can tell us whether the participant is behaving according to a scenario where the weight is 1 or a scenario where the weight is 0.5. Yes. Yeah. Mm-hmm. Mm-hmm. Information. Yes. So the incompatibility that Lauritz is pointing to is when we're working with these models, is the rate at which the participant picks red a measure of their estimates of the underlying rate, or a measure of how confident that there is at least some skew in the red direction. And that's where I've been revamping the course, and we're gonna learn a new ways of doing things, but you're very free in the assignment to pick whichever you want, which is the beta distribution trick, right? So we have that a posterior probability can be modeled as a beta distribution, right? We've seen it before. The beta distribution is a distribution that has two parameters, alpha and beta, and I'll show what they are in a second, and it outputs a number between 0 and 1. So the two parameters in the beta distribution is that alpha is the number of ones that you've observed, let's say the red marbles, and beta is the number of zeros. And this information preserves both if there is a skew, more red than green, but also how many, how reliable the sample is. So this means that we can easily update the distribution instead of having to draw the full distribution by adding our new observations straight on to the parameters, right? If we observe 3 more green out of 3, we're just going to add 3 to beta. And that preserves all the information. So if we assume, right, a prior alpha of 1 and a prior beta of 1, uniform, we don't know anything before we start. Right? We simply update it by saying the posterior is equal the beta distribution with 2 parameters. Alpha, the new alpha, posterior alpha is given by previous alpha plus the red marbles, and the posterior beta is given by the prior beta plus the green marbles. Right? And again, it doesn't need to be prior and posterior in likelihood. It could be 2 sources of information. And so we don't need to keep in mind the full distribution. We can just pass the updated parameters as counts and add the new info as it comes. We get the full distribution as needed, including all the uncertainty. At that point, we can have a decision rule that, for instance, follows what was before on the left. That's saying as soon as there is even a slight skew in how often red comes up, it picks red, or we can have a decision rule that follows more the actual distribution of the underlying rate. Is this clear? Right, we'll see the code, right? I know that without code is never fully clear, but as an intuition, yes. Yeah, that's the smart thing. It's a very simple operation, very little information that you need to keep in mind, and it just keeps all the information in. Sometimes what you then have to do, as we will see, is to make assumptions and turn the structure of the experiment into something that can be modeled as counts, which is not always. So how rational is, okay, now we have this idea that we can implement a rational Bayesian update of belief using log odds or using the beta distribution, but we want actually to be critical as usual and say, why are they always talking about Bayes as a normative model, as the rational way of integrating information? Right? Because we could imagine that actually just taking evidence at face value is not the most rational way of doing things. So should you trust the information that you got from that idiot who used to teach you method 3 or from the impressive teacher of advanced cognitive modeling? Right? You should probably adjust your weight. Should you get medical advice from your doctor or from your primary school friend? Right? And this is actually a non-trivial decision because we all know that there are certain cases in which if your friend has had a lifelong experience with a disease, probably knows more about how to deal with that than your doctor. But it's just to say that we shouldn't just take all the sources at face value. And indeed, there's lots of literature on wary social learning. There's a really neat chapter in Cultural Evolution in the Digital Age that tries to make this case for, being critical of all this literature on misinformation. So what we want to do is we want to go from the simple, rational Bayesian agent to an agent that can differentially weight the evidence sources. Right? So if we think about the log odds model, right? Here we had the outcome is given by source 1 plus source 2 plus eventually a bias if we want. And what the weighted Bayes would do is it would simply add a weight, as we've seen. There's a weight for source 1 and a weight for source 2. Again, we are, for the purpose of the progression, assuming that those weights don't change over time. And we can think about what is a meaningful scale for the weight, right? For instance, we could say that 0 to 1, where 0 is we don't consider the information, it just gets annulled. To 1 is, we take the information at face value. Technically, we could also include values that go below 0. For instance, if Josh tells me something, then I'll take the opposite stance, right? That would be a negative weight. Or above 1, which is overweighting the information, right? So if I really trust Victoria's gut feeling and she says, maybe we should go for B, then I'm just going to say, yes, B, right? I really believe that we should go B. If we want to add these to the weighted beta, it's not that tricky, but let's just see it, right? We have the simple beta integration has the posterior, which is more or less like a beta with your prior alpha plus counts of the first category, your prior beta plus the counts of your second category. And what we do is, I actually made it more complex than it needed to be. So yes, sorry. Consider it alpha plus W1 times counts 1 and beta times W2 times counts 2. Yes. Here I went a step beyond and say, what if we have a prior and 2 sources of information? So the weights scale the effective sample size of the evidence, making their contribution more or less confident, right? If you think we're multiplying counts, so basically we're saying if I'm overweighting Victoria's opinion, right? She tells me I've sampled 1 marble and it's red. I think that she's an excellent sampler. So I'll say I'll multiply it by 2 and I'll change my belief as if she had sampled 2 marbles and she had 2 red marbles. Right? And this is kind of silly in this specific context, but that's how it works. It makes that distribution of the evidence more or less narrow, right? Higher weight, more narrow, lower weight, less narrow. Again, we have a scale that's very similar to the previous one, right? 0 evidence is ignored, 0.5 evidence is treated as half informative, 1 evidence is taken at face value, 2 evidence is treated as twice as informative, and negative is doing the opposite of what the evidence says. Do I need to do this? Yeah. So this is something that came up as I was building the course notes. So if we use a deterministic decision rule, right, let's say as soon as there is more evidence for red, I'm going to pick red. Then what happens is that if the relation between the 2 weights is constant, the actual values of the 2 weights don't matter, produce the same result. Let's say if the weight for 1 for my own sampling of the materials and the weight for 2 for Victoria's sampling of the marbles is 2, right? That will produce the same decision as if I'm taking both of us at face value. And therefore, the Hamiltonian Monte Carlo will go wild and just get stuck in those areas. And then we would need to constrain them by saying that the weight of 2 is actually going to be 1 minus weight 1, right? So that there's only 1 parameter that can move. If we use a probabilistic rule, actually, then both weights being 2 is going to be different than both weights being 1, because higher weight will mean narrower distributions and higher confidence in the agent. So weight 1 equal 2 and weight 2 equal 2 will yield the same expected value, but lower variance. We don't expect the participants to show a broader range in their behavior than while weight 1 and weight 1 will give us a broader range of behaviors. So we can use these ideas to model a bunch of different experiments. So for instance, right, this is an expansion of the Polya urn in the paper that was in the recommended reading for today. You have to decide what's the next marble going to be. And you see your own sampling in your hand, and then you see 4 different people telling you whether they're picking red with high confidence, red with low confidence, green with low confidence, green with high confidence. And we are interested in how this sort of information influences the participants' choice. So we have that the outcome follows a binomial distribution. We can model it using the log odds. So for instance, we could take the sampling, and say that n red marbles out of 8 with 0 red should be low evidence for red, 8 red should be high evidence for red. And so we could simply redefine it on a probability space as red plus 1 divided 10, so that 0 red is something like 0.1 and 8 red is something like 0.9. Right? Then we can put it in log odds and we can do all the usual stuff. However, we can also, so others would be equal, right? We have 4 of these. We want that the first one is going to be 0.1, the last one is going to be 0.9, and then these 2 are the intermediate values. However, we might also want to use the beta distribution. And let's take, if it's the self, it's easy, right? How many red, how many greens? If we take the other, what we can do is we can say, well, there's 4 possible values. So what if we go from 0 to 3, right? So confident green is 0 red marbles. Unconfident green is 1 red marble out of 3. Unconfident red is 2 red marbles out of 3, and confident red is 3 marbles out of 3. And of course, you could stretch it. You could make different values, but this would be the most obvious way also to reflect the fact that we're not seeing the other person's sample. So giving it the same scale from 0 to 8 would sort of betray the fact that there is an intermediate step. We can also have you ever gone through the imitation inhibition task? Probably, right? But basically you have, you're keeping your fingers on the keyboard, the index and the middle finger, then you see on the screen a number. If it's 1, you raise your index finger. If it's 2, you raise your middle finger. And at the same time, on the screen, there's also another hand that's doing either the action that you need to do or the action that you shouldn't do. And this is a test that has been designed to sort of discriminate how much information from other people is leaking into your decision, even when it's explicitly not relevant, right? And people tend to be faster when the action of the other is congruent, and they tend to be slower when it's incongruent. And so here, the way we can model it is we can have the outcome is binomial, the index versus the middle finger. The predictors on log odds would be 0, 1 if the evidence points towards the middle finger, and 0.9 if it points towards the index finger. Again, why are we not going to 0 and 1? Yes. Yeah, because 0 is infinite. And basically, if we see a source telling us infinite, then we shouldn't even look at the other, right? And that's not interesting. If we're looking at the beta, right, it's a 0, 1. It's easy, right? It's actually mapping straight on. If we take as an outcome the reaction time, that's going to be a bit more tricky, but it's doable, right? So we can invert the reaction time so that the slowest is close to 0, the more uncertain, right? The index choice is plus positive values. The middle choice is minus negative values, right? And then we can sort of give it a specific scale to put in on a, how many, like a very fast reaction time, how many red marbles should it correspond to, right? How strong an evidence should it correspond to? And there is lots of literature that is mapping the reaction times to how confidence works. So that could be used. So the idea is that we can have a bunch of different tasks that can be modeled using this basic principle of Bayesian cognition. And assignment number 3 is going to be an assignment called social conformity. You might also have gone through that. But basically, you're shown a face, and then you need to rate how trustworthy that face looks from 1 to 8. Then you go through 150 something faces. The details are in the assignment instruction. And then you do, oh, sorry, I forgot one important piece. You see Ivana's face, you give her a trustworthiness score, and then the computer tells you, look, right, the average of your peers actually gave 2 points more, or 2 points less, or the same. And since you're very experienced experimenters, right, we can use that to simply generate all the possible contrasts given all the possible ratings of the participants. Then people go through some other task for an hour. And then in the sneaky version of these experiments, they're told, oh, shit, right? We didn't save your logs. Could you please redo the social conformity task? And then you're shown these faces again, right? In a different order. And then we're interested in how much the group rating that you were exposed to has impacted your final posterior rating, right? Does that make sense? And let me see what I have here. Well, and so the goal of the assignment is really that you now will see some code, and there's course notes on code on a simplified version of this first experiment. And you need to figure out how to apply the same principle to a different experimental setup, which has impact on the way you code your simulation, but also on some aspects of the model itself. So we have 8 minutes. So we'll just see the beginning. What we're going to cover in the lecture today and tomorrow and next week is Holia urn with varying proportions of green and red marbles, and in the course notes is blue and red, I think. At each trial, the urn changes. No learning is possible. We'll cover some learning at the end of next lecture, but not for the assignment. At each trial, you sample n marbles, say 8, and we call that source 1. At each trial, another participant samples hidden to you the same amount of marbles and communicates their guess as to the next ball, next marble, including their confidence, source 2. Right? And then We can decide, and we'll see example of both, whether we rescale source 1 and source 2 in log odds, or whether we keep the amount of marbles in the self or source 1, and we rescale the other as 0 to 3. And so the experiment in this case is built so that you get all combinations of source 1 and source 2 10 times. And we can simulate the simple beta. We have that it takes an alpha prior, a beta prior, number of blue marbles, because I copied it from the course note, so that wouldn't be on black background. The total number of marbles that are sampled, the number of blue marbles in the other source of evidence, and the total number of marbles in the other source of evidence. We can calculate the red, the missing one, just by saying total minus blue in both cases. And then what we have is that the posterior for the alpha is just given by the prior for the alpha plus blue 1, what we see in our hand, and blue 2, what the other is saying. The posterior for the beta is whatever is in our beta prior plus the amount of red marbles we see in our hand and the amount of marbles that we assume being in the other person's hand. And then if we want to have, for the simulation, an expected rate of picking blue versus red in this case, we have the formula that says that the posterior alpha divided the posterior alpha plus the posterior beta is the expected rate, which should make sense to you because basically we're saying what's the total amount of marbles at the end, posterior ones plus posterior zeros, which proportion of that is ones. Does that make sense? This is for the simulation. In the stand, we'll try to keep all the information in place. This is how the model behaves in different kinds of scenarios. With the dashed blue, we show the direct evidence, the own sampling. With the dashed red, we show the other evidence. And in purple, we show the posterior estimate that we get from that. And so we can see that there can be very asymmetric distributions. So on the first plot on the top left, we get that red is basically saying that there's 3 blue marbles. On the left is 3 red marbles, right? And the blue is telling us that there's something in the same direction, right? And then we get the so direct is 1 blue, and social is 0 blue. And then we see that our belief in the next one being blue gets strengthened. The opposite is true here, where there's 3 blue for the social and 7 blue for the sampling. If we go in intermediate cases, then the evidence in different directions get integrated somewhat in the middle. And we can get an overview of all the possible values. Here we see that on the x-axis there is the number of blue marbles in direct sample out of 8. And on the y-axis there is how often the agent picks blue marbles. The first red line is what happens when the social evidence there says clearly red. You can see that with more blue marbles in the direct sample, the propensity to pick a blue increases, but it starts very low, very skewed towards red, and it barely gets above chance at the end, but to a certain extent it does. If we have the other person that says clear blue, again, we start picking red because our evidence says 0 blue, but very quickly we shift to picking blue. And if we were to do the logouts model, actually something slightly different would happen. Since we're moving in a logout space, what would happen is that we get nonlinear phenomena, right? And that's where we can see what people are actually doing and see what actually matches our expectation better. And then we could also do model comparison on that. If we take the binomial with weighted, the beta model with weighted, am I saying it wrong? Yes. This is the single agent again, the rational agent in STAN. It has as many rows as are needed, the choices that the agent is making, how many blues in their hand at every trial, the total number of marbles in their hand at any trials, how many blues in the other, and the total amount of marbles in the other. And then we go on a trial by trial loop, doing exactly that operation that we were showing before. It's just the STAN code. And here, because I was in a hurry, I wrote, instead of alpha prior and beta prior, I wrote 1, but I should go back and write it as alpha prior and beta prior. And then there's the generated quantities. In log odds, it's very similar. We just have the model that we've seen before. I should dismiss this. And when we do the weighted beta, is the equations that we've seen before, right? That the blue and reds in our hands get weighted by our weight for our own sampling. The blue and reds from the other gets weighted according to the weight social. And everything else is exactly the same. And maybe I should specify that the beta distribution doesn't really care whether alpha is 1 or 1.5, right? All values work. And I think this is just how we can visualize the way that the decision moves. You can see on the x-axis the weight for direct evidence, on the y-axis the weight for social evidence that we can manipulate. And in the first scenario, we have strong evidence for blue and strong social evidence for red. We can see that according to where the weight for the evidence is, our decision boundary shifts. As we increase the weight for social evidence, our boundary shifts towards the right. If we have, on the contrary, weak evidence for blue in direct and strong evidence for red in the social evidence, right? This is the same setup, and we see things being skewed that way. They're not perfectly symmetric. This was the key point I wanted to make before I let you go, because the evidence from the other is less confident, right? It's out of 3 instead of out of 8. So the decision boundary in the lower one doesn't go as much down as it goes up in the other one. Even if there is strong evidence for red in the other, given we put implicitly less weight on the other because of the number of samples, then it doesn't influence our decision as much. And with that, we'll stop, and I'll see you tomorrow. This is just how it looks all over the place.